Okay, this is Circular Extensions HL Part 2. We barely got started and we already moved to Part 2. Okay, let's say you're here now. So you've gone from here, you're gonna, and now we're here. So this is interesting, right? Your forces, gravity is going to be straight down. I'm drawing it bigger, but. And which way is your normal force now?
It doesn't exist. Center impact.
Does it have to exist?
Yeah, if it's in contact with the...
Yeah, because you have the velocity that's
No, but there's nothing pushing it.
There's a situation actually, Jeffrey. There's a situation where Jeffrey's correct, where it actually doesn't have to exist. What situation is that? Say it again, Colin.
When there's like no force, when it's not.
Yeah, okay, there's no force inwards, but what situation does that have to be in?
Exactly 90 degrees.
Remember, circular force is what formula? Not banana. mv squared over r, thank you. So you have to have a velocity, and if you do have a velocity, you have to have a centripetal force. If there's no force towards the center, you're not moving up around this ramp. It cannot happen.
So it's like pop up and all.
That's correct. Can't a golf clap for Kenta. So if you fling this thing and it goes, then right at the top, there's zero centripetal force because it's not going to keep going in a circle, right? It's just hanging there for a sec. And then there's no force, and of course, what does it do right after it hangs? It starts to come down. And then right away you have a small normal force. And as you fall back down, that normal force will grow, right? Okay, but let's say we're keeping going here and we do have a force. We have some normal force this way. Yes, Jeffrey?
Oh, I was wondering what, like that ramp example I read, like, does the object stop like at 90 degrees, like completely parallel?
Completely parallel, yeah. Yeah. For you to have no normal force there, you would have to do that. And again, if we had a jetpack and these two were, if you had another force up here and these two were equal, then you could maintain perfect constant speed all the way around, right? As it is now, what has to happen? You have normal force, so you have you can have a circular motion, but is it a uniform circular motion? No, you can't go at the constant velocity, right? So where's your acceleration? It's downward and inward, which is like, this is my FG, and if you add our normal force like that, you're going to end up with an acceleration like that. What does that mean for our future movement? Sana? Go ahead. Yeah, that's exactly right. Very good. Goes up the ramp, it keeps going, but it's going to slow down. The linear speed is decreasing. Okay, I won't make you draw another circle, but let's say, so this is kind of still moving, but slowing down. I gave you a question the other day with a loop-de-loop ramp, and I said, how high do you have to be to start, right? To just make it around. This is kind of an interesting situation. So when you get to the top, the very top, if you're going to just make it around, what is the situation? Turn to the person beside you and decide. Aveen, what do you think? Are you just posting today? You can post today. You're struggling with your email. Okay. something else in your mind. Okay, carry on. That's fair. That's fair. We'll absorb as much as you can. Maziar, what do you think?
I think you can fix
Hi,
it.
good morning. How are you? Good. What do you think's happening here at the top?
At the top,
Yeah.
what do you mean what's happening in regards to what?
What is the thing doing?
It's gonna fall a bit.
Oh, it's gonna fall a bit. Okay, so if it comes off the track, are we dead? Like, is there any chance?
Yeah, pretty much.
We're gonna. It could be bad, right? Because if we go like this and we fall a bit, we come off the track, then we're falling. We're gonna be parabolic, right? Which is steeper than circular. So if we come off this track, we're not gonna like come off a bit and then like come back up and hit here and go around, right? This is gonna be like one of those TikTok videos where the guy's trying to do the loop-de-loop and it falls. And you're gonna fall until you hit something coming back around here. So you're gonna come off and you're gonna case it on the bottom of the ramp, right? It's gonna be bad. So if we wanna just make it around, we can't come off the ramp. So what are the forces involved if we're gonna stay in contact with the ramp,
Normal.
but just barely?
So there's no.
Kenta?
Normal force?
Is there a normal force?
Well, it has to be.
So yeah.
There has to be.
Because if you have velocity, aren't you supposed to have normal force?
Okay, so you're like right at the crux of it. So Kenta's, I know where his mind is going. He's going, you need a force this way, otherwise you can't do circular motion. And you're absolutely correct about that. But we don't need a normal force.
Because gravity is pointing.
Because now gravity is our centripetal force.
So for that fraction of a second, there's just gravity, it changes the.
And now your mind is working very well today, Kenta. So just at this instant, you have no friction. You have no normal. You have no normal. So just gravity is providing you your centripetal force, right? This is your net force up here. There's no other force. So actually for this instant, what's happening to your linear speed? Is your speed zero?
Just like stay there.
Colin went like this, and there is a zero in there, but what's zero?
Acceleration.
Yeah, your linear acceleration. So this is where the HL and the SL divide. In the SL curriculum, we just talk about acceleration, right? To go around a circle, you need an acceleration down. And you just keep this linear speed the same, right? And v squared over r is a thing, and it's all good. In HL, we talk about changing linear speed. So if you're gonna change your linear speed, then we can come in here with a high speed, and that linear speed can slow as we go up to here, right? And our normal force is gonna change amounts as we go. And when we get up to here, you have just gravity, no normal force. Can I have zero velocity right here?
No.
If you have zero velocity, what's gonna happen?
You're falling.
It's gonna fall straight down, right? So if that happens, it's bad. So we need some velocity. Could we calculate what it is?
Yes.
Yes. So even in a situation where your linear speed is changing and you have this acceleration that's tangential to the circle, right at this point, none of that matters because you have to have a constant velocity here. So the zero that Colin was saying was zero linear acceleration. So even though you have centripetal acceleration, this linear speed is not changing for an instant, small space. Yes?
Why can't you be accelerating as like the linear acceleration?
Well, you could be, but if you were accelerating, you would have a normal force. And then you would go through here faster.
Oh, okay, never mind.
Like you would go through the point with an extra bit of force, that would hold you through. Which, if you do this, this is what you want to do. Like if you're driving a car or a bike or whatever, and you're gonna do a loop to loop, you want a normal force up here. Like you don't want to just barely make it, right? You want to be going fast enough that when you go around, the track is actually pushing you downwards, and then you're gonna have better probability of making it around, right? But in this situation, we want to know what's the height we have to go from, or what's the velocity we need to just make it around. Because then if we calculate that, we know this is our minimum velocity or our minimum height, and we're gonna have to be higher than that, right? Does that make sense? So if we calculate it with no normal force, our linear speed is unchanging, which means our mv squared over r is equal to mg. And if you know that mv squared over r is equal to mg, yeah. So can we write in the middle of the circle? So in that situation, Fc equals mv squared over r. That's supposed to be an r, sorry. My v's and my r's end up looking exactly the same. And that is also mg, right? So in that situation, v squared over r is equal to g. Yes? And so our v, what's our v equal to? Good, so we can do gr square root. And so if you know your radius of your circle, you can multiply by g, take the square root. That's the minimum velocity you need up here.
Can you just do energy?
Now, this has been done before, where this calculation's been made, and the person enters the ramp with this velocity. That's why, like, poor physics can really hurt, right? It would be bad. So you have to be going that velocity at the top. Yeah. So you gotta be going faster when you enter, right? Because you're gonna slow down. We realize you're gonna slow down to that velocity up here. So Kentis just said energy. So that's how you find out, right? You need this velocity at the top. And so you can put this V into the formula for kinetic energy at the top. That has to equal your potential energy that you have.
Well, plus the potential energy.
Yeah.
Do you slow down because the kinetic energy is being turned into potential energy? Like,
Yeah, that's absolutely correct. Yeah. There's no friction, so if you come in here with kinetic, you're gaining potential energy, as Luke said. It gets really simple with energy, right? You're gaining potential, so your kinetic has to come down. And of course, in real life, you have friction too, right? So you can calculate we're losing this much, but that gets complicated, right? Why does the friction thing get complicated?
Because then you would have
V.
force.
Hard to measure the energy because there's friction.
Why?
because your force
normal force
changes.
changes.
Your normal force is changing. So friction is mu Fn, right? Up here it's easy. It's 0, right? But here, all the way along, it starts easy because Fn is the same as mg. So you just do mu Fn and that's the friction you're burning, right? But as you move up, that force gets less and less and less and less and less. And so your friction gets less and less and less. Which is nice, but it's not enough. You gotta start with more energy. So anyways, if there's no friction, kinetic energy is turning into potential, right? So you gotta have enough kinetic energy at the beginning to negate this gain in potential. But is your kinetic at the beginning gonna equal your potential at the top?
No, because you're moving.
Correct. It cannot, right? So that's the rookie mistake is you go, well, okay, it's the same as science 10 and it's, half mv squared equals mgh and that's the end. But of course you have to be moving at the top, right? Because our v has to be root gr. So it's root gr velocity has to be this. Let's put this into our kinetic energy formula and see the kinetic energy we need.
1/2 mg.
I'm just gonna do a new sheet here. Is my video still working?
Yes.
Okay.
Now it's
Okay, so we said that V has to equal square root of GR, and this is at the top of our Can you see that? At top of circle, if we just make it around the loop. So if we just make it around the loop, this has to be our velocity. And so, of course, EK is half mv squared. And so if we do half mgr squared, then we're going to have 1/2 mgr. So this is the kinetic energy we need at the top. And so how would we calculate the energy we need at the bottom?
Kinetic energy at the top plus the potential energy at the top.
Perfect. So so if I say EK, maybe I should put EK at the top and EKI. Or maybe I'll say bottom. The kinetic energy at the bottom has to be half mgr, which is the kinetic energy we will need at the top, plus we have to negate that mgh. Okay, so if we want to calculate our V initial, or maybe I'll say V at the bottom, that has to be squared, is equal to half mgr plus mgh. And what can we do there, mathy people?
H is 2R.
Yeah, h is 2r, so this is going to be 2r. The height will be 2 radius of the circle. That makes sense, right? So when you're at the top, your 2 radius is 2 radii higher than you were before. What else? What can I do with this?
Cancel.
Image.
Yeah, my masses are gone, so we can say half v squared equals half gr plus g2r.
Combine like terms.
And yeah, we could do if we wanted to find our velocity. It depends what you want to find, I guess. If you want to find your velocity, you would be gr plus 4gr, right?
Which is 5GR.
Which is 5gr. Oop.
Shouldn't that be V squared?
Say that again?
Shouldn't that be V
Yes.
squared?
I haven't done the thing yet. I was gonna square root it all, but yeah, maybe I'll just do that. 5gr and then v equals the square root of 5gr. So that's the velocity that you would need coming in, right? And of course, I asked you guys how high we release from, so you just have to make this kinetic energy that we got in the beginning, you have to make that equal to the mgh at the beginning. And it comes out to 5/2. I shouldn't have told you that. You're still working on it. Well, yeah, I'll tell you. The answer is 5/2 r. The height has to be 2.5 times the radius of the circle. And you should be able to work that through and get that.
Mr. Husband,
Yeah, Jeffrey.
is it possible if the IB Council can make an announcement at a suitable time?
Yeah, do it. Well, how long is it?
That's 30 seconds.
Okay. I'm gonna pause part 2. This is video part 2. And the IB Council can speak.
So